I welcome you to another video on compilers. This video is loaded with lots of useful information. Number one, this video we will learn that what is the difference between SLR parsers versus LR0 parsers. Number two, we will learn how to create parsing tables of both of those parsers. Number three, and maybe most importantly, we will learn how to resolve conflicts. In SLR and LR parsers. So let's start. Both SLR and LR0 parser are based upon the same automaton. That means LR0 DFA is used by both of those parsers. However, in SLR, our conflict resolution strategy is better. So, SLR parser accepts a larger set of languages as compared to LR parser. The creation of parsing table in those parsers, because of their conflict resolution strategy, is different. Before we start making parsing tables with an example of both of those parsers, let me first describe what I meant by conflict. There could be two kinds of conflict. Number one is shift-reduce conflict, and number two conflict is reduce conflict. In this case, we could have performed two different actions. One action could be shift and one action could be reduce. Whereas in this case, we can do two actions, and those actions are reduce, but two different kinds of reduce. Let's make it more clear with a high-level sketch. So, let's say we have created LR0 automaton, or in our case LR0 DFA, and a state of DFA is such that it has two different reduce statements. For example, it has a statement A goes to X, Y dot. A reduce statement is a projection where this dot is at the end of the projection. That means we have seen the whole projection and we can use that projection for reduction. I will explain it better with an example, but for the moment we are only considering a high-level view. So another reduce projection in this state could be maybe B goes to alpha, beta, and dot must be at the end. So in this case, this state has reduce conflict. That means we can do two different kinds of reductions using this state. Similarly, we could have shift-reduce conflict. For example, consider another state of a DFA where I have one possible shift path. So I have a projection A goes to X dot Y, and on Y I can shift to some other state. And I have also a reduction statement in it. B goes to alpha beta dot. In this case, this state of LR0 DFA has shift, reduce, conflict. However, please note that if our LR0 automata has conflict, it doesn't mean that our parsing table will also have a conflict, because we will use some strategies for the creation of parsing table that can potentially resolve those conflicts. However, if our parsing table also has a conflict, then we can say that such a grammar is not LR0 grammar, because even in the parsing table of LR0 we have a conflict. Similarly, if we make SLR parsing table and it also has a conflict in it, then we can say our grammar is not SLR grammar. But how can we know that if our parsing table has a conflict? We will do an example, but for a high level view, if a same cell of my parsing table has two different actions in it. One is shift action, say shift 1, and one is reduce action, say R2, which is reduce to projection 2. Then because of two different actions in a same cell of my parsing table has a conflict. And if this parsing table is of LR0 parser, then I will say that my grammar is not LR0 grammar. And if this parsing table is of SLR parser, then I will say that my grammar is not SLR grammar. So we might have conflicts here, but we will do some conflict resolution strategy here and then create parsing table. So it's possible that I have conflicts here, but in parsing table I have no conflicts. In that case, I can use such a grammar for my parsing. Enough with the high level view. Let's do an example. In this example, first we will create LR0 parsing table, and then we will create SLR0 parsing table. So this is my example context-free grammar. To make the parsing table of LR0 or SLR, the steps are similar. First, I have to augment that grammar by introducing a new start symbol. Let's call that start symbol S bar, and that new start symbol goes to the previous start symbol, which is L. Afterwards, I have to make LR0 automaton of this augmented context-free grammar. In a previous video, I have already explained all the steps involved in the creation of LR0 automata. Therefore, in this video, I am going to create LR0 automata quickly for you without explaining those steps. If you have some doubts, go back to the previous video. So, I have created LR0 DFA using the steps that I have explained in the last video. Now, I have to create parsing table. The parsing table will have three parts. First part is states. Our second part of the parsing table will be actions, and our third part of the parsing tables will be goto. In the state part, we will write numbers of all the states. I could write here I0, I1, but I prefer to write only integers. So we have 7 states, so I will write 0, 1, 2, 3, 4, 5, 6 and 7 here. The action part is related to the terminals of my grammar. So my grammar has ID equals to and integer, the 3 terminals. However, I also have to write end of the input marker $sign in the action part. In the goto part, I will write all the non-terminals. However, I will not write the new start state that I have introduced in the beginning. I will only write non-terminals of the original grammar. So my grammar has 3 non-terminals, which are L, S and E. First, I will write only shift and goto. I will not write reduce action in my table. Please note that LR0 parser and SLR parser are different only in the context of reduce actions. They are same in the context of shift and goto. So just first concentrate on writing the common part of both of those parsers. To write shift and goto in this table, we only have to look at those links and write number based upon those links. For instance, from state 0 on ID, I go to state 3. So I will write here S3. I will write shift instructions here where I don't have to write shift, I can just write the state number on this part. Because in this part, I will also have reduce actions and I have to differentiate between shift and reduce. So here in this part, I will write S for shift and R for reduce. Whereas in this part, I will have only goto instructions, so I will only write the state number. So I'm done with this link, and this state has 3 links. Therefore, this state will have 3 entries in this row. The second entry will be that from state 0 on grammar symbol S, I go to state 2. So I will write here 2, and then from 0 on L, I go to 1. So I will write here 1, and so we will fill this whole table in this manner. So from 1 on $, I go to this special final state of my automata. So I will write here except. This is a special action which basically accepts my input string. Then from 2 on L, I go to 7. From 2 on S, I go to the same state. From 2 on ID, I go to 3. I am done with this also. Now let's look at this. From state 3 on equals to, I go to state 4. And from state 3, I don't go anywhere else. So I'm done with state 3. Now we consider state 4. From state 4 on integer I go to 6. On E I go to 5. I'm done with this. Now I consider the state 5, which is this one. I don't go anywhere, so no entry in it. On state 6 I don't go anywhere. On state 7 I don't go anywhere. So that's it. These are all my go to and shift actions in my table. Now I have to add reduce actions in this table. Here LR0 parser and SLR parser differ from each other. That's how to add reduce action in the table. Let's first consider LR0 parser. First, we have to number our productions of context-free grammar. So I number this production 1, this 2, this 3, this 4. I will not number this production. This was a special production which I will not reduce to. I will only accept this production which I've already done here. So I will not add any number to this production. Now, in the second step, I have to look all of my states and find these productions with the dot at the end. Because only when you have dot at the end, then you can reduce some production. Because you have seen the whole production. You can't reduce when you have seen half of the production. So this dot is at the end, but I leave it as it is. This is a special production. Here I have no production where dot is at the end. Here I don't have any reduced production. This is a reduced production because dot is at the end. So I mark it with a red line. I don't have any other reduced production here. I don't have any reduced production here either, but this is a reduced production because dot is at the end. So I will mark it with the red chalk. This is a reduced production because dot is at the end. So I will mark it also with the red chalk. This is also a reduced production. I mark it also. Now for LR0 parser, the rule is that if you have a reduce action, then you add that action in all the cells of action part. So in this case, that means for this row, I have to add L goes to S in all of those cells. Because L goes to S has number 1, so I have to add here R1, R1, R1 and R1. Obviously you can see a shift reduce conflict here because both of those actions are in a single cell. So we can say that this grammar is not an LR0 grammar, but we will still continue and fill this table quickly. So for this, which is R2, I have to add here R2, R2, R2 and R2. Done with this. For this, which is R4, I have to add here R4, R4, R4 and R4. And for this, which is R3, I have to add here R3, R3 and R3. So that's it. This is my LR0 parsing table. However, it has a conflict which cannot be resolved for LR0 parser because this grammar is not LR0 grammar. So now I will remove all of those reduce actions and then we will repeat this process for SLR parser. For SLR parser, I have to add L goes to S which is R1 only in the cells of follow of L. So I have to first compute follow of L and then add R1 on the tokens which are in the follow set. It is because we can only reduce to those tokens which are in the follow of L. We can't reduce to the other tokens because in the stack of our parsing algorithms only those tokens will come and only those tokens can be reduced by L. So now let's compute follow of L. So follow of L according to this is equals to $. Therefore, I will add R1 only in this cell. Therefore, in this case, I don't have any conflict in this row. Similarly, I will not have any conflict in the other rows because they don't have any shift statement anyway. But still, we can quickly add those instructions also. So I once again has to find follow of L, and I know that follow of L is $, so I have to add R2 also here, and in this case I have to find follow of S. Follow of S is equals to follow of L, which is also $. So I will add R3 also here in this cell. Similarly, I will have to compute follow of E, and for this simple example, follow of E is follow of S, which is follow of L. So I have to add R4 also in this cell. And that's it. This is my SLR parsing table, which has less reduced entries as compared to the LR0 parsing table. So it has less chances of having conflicts. However, SLR parsing tables also have lots of conflicts for real context-free grammars which are used by the programming languages. So in reality, we rarely use SLR or LR0 parsers. We use CLR and LALR parsers more often. And that we will study in the upcoming videos. So stay tuned. Bye.